All right, in this lesson, we are going to find key attributes of exponential functions. And when we talk about key attributes, we usually mean intercepts and max and min on intervals. So first of all, some exponential functions we've looked at are exponential functions that are growing or increasing. And then we've also seen some that are growing upside down, which would be a decreasing function. We've also seen a decreasing decay function. We've seen an increasing decay function. So the main thing we care about here is whether it's increasing or decreasing. So always imagine a person traveling left to right, and notice on this red curve, it's going up, so that's increasing. Notice on this red curve, we would be going down the mountain, and so that's decreasing. Okay, so decreasing. Increasing. This blue graph is decreasing. This blue graph to the right is increasing. Okay, that will help us when we are trying to find max and min on intervals, because that actually makes it really easy to determine which point to plug in. Okay, so starting with x-intercepts are always where y is 0. Okay, and so as an ordered pair, you're going to see some x value when y is 0. Other names is roots. Another name would be zeros. Another name would be solutions. All of these refer to x-intercepts. Okay, and so algebraically, if we are trying to find the x-intercept, we are plugging in y equals 0. So anytime you see x-intercept, doesn't matter what function you are working with, you are plugging in y equals 0. Okay, not y, not that x, sorry. 0 for the y. So that would be over here on the left. And so my equation would still have x involved, and we have to solve for the x. So our first step is to add 4 to both sides, isolate your exponential expression. And then from here, if you notice that you can get a common base, for example, I can rewrite this 4 as 2 squared. That'll help you solve for your exponent without using logs. Okay, and so now that my bases are the same, I know my exponents have to be the same, and so that leaves me with the equation 2 equals x plus 3. And so then I would just subtract 3 and get -1 for my x value. And so you always write your ordered pair as -1, not -1, but x comma 0 as an ordered pair. Okay. And then to find the y-intercept, that is always where the x is 0, so the complete opposite. And so you're going to have 0 in the x spot and some kind of y value in the y spot. And so if we are trying to find the y-intercept, we plug in x equals 0. And it doesn't matter what function you're working with, that's always how you find the y-intercept algebraically. Okay, and so that leaves me with 2 to the 3rd power minus 4. 2 to the 3rd power is just 8, and then 8 minus 4 is 4. And so when we write our answer as an ordered pair, 0, 4. Okay, and so there's a note up here, depending on the location and relation of an exponential function to its asymptote, it may not have an x-intercept. For example, if the asymptote is 0, it's never going to cross the x-axis, but in this case, our function has been shifted down, and so it does cross the x-axis. Okay, and so the algebraic method I just showed is plug in 0 for the y to find the x-intercept, and then solve for x. That's a little bit harder because you actually have to solve an equation. When you're finding the y-intercept, you're plugging in 0 for x, and you're just simplifying or evaluating the function. And so you can say evaluate, or you can say simplify until you get a number. It's just number crunching. Okay, so now we're going to talk about max and min on an intervals. And so when you are trying to find a maximum, you always only write the y value, the output. Okay, and so for an increasing function, a function that is increasing from left to right, the maximum will occur at the right endpoint. Okay, for a decreasing function, the maximum will occur at the left endpoint. Okay, and so for example, I'm picturing what this graph looks like. It has a base of 2, which means it is going to grow, and it hasn't been reflected. There's no reflection outside, there's no reflection on the y-axis, and so it's going to grow. And so I can also picture that the horizontal asymptote is at y equals -4. Okay, and so I'm going to make that a dotted line because it's invisible. And so my maximum for this function is going to occur at the left endpoint. We're looking at the interval from x equals -4 to x equals 3. Remember, those are always x values. So from x equals -4 to x equals 3. So picturing this, I would have -4 over here, and I would have +3 over here. Because this function is growing as I go to the right, the point at 3 is going to be higher than the point at the x equals -4. Okay, and we're obviously getting closer and closer to that horizontal asymptote at y equals -4. Okay, and so this specific question is asking for the maximum, and so having this picture, I know exactly which point to plug in. I need to plug in x equals 3. Okay, and so we plug in x equals 3, and we get 2 to the 3 plus 3 minus 4, which gives us 2 to the 6th power minus 4. And that gives me 64 minus 4, which is 60. Okay, and so your maximum value occurs at x equals 3, and the value is 60. And so if it's just asking for the max, you would just say 60. Okay, for a minimum, for an increasing function, that means the left endpoint is going to be where the minimum is. And then for a decreasing function, that should say minimum. The minimum will occur at the right endpoint. Okay, and so here we have the exact same function, but now we want to plug in the left endpoint because we are looking for minimum. So plugging in the -4 would give me y equals 2 to the -1 minus 4. And 2 to the -1 is 1 over 2. It's the reciprocal. Anytime you see that negative exponent, that means it's underneath the fraction bar. And 1/2 minus 4 is -3.5. And so the minimum occurs at x equals -4, and the value is -3.5. All right, so now we are going to look at some different functions, but we are still going to find the x-intercept, the y-intercept, and then the max and min on given intervals. And so if the answer is not a whole number, we're just going to round to the nearest tenth, so 1 decimal place. So we may need our calculator, we may not. All right, so for this first example, it says find the x-intercept. Okay, so for an x-intercept, you're plugging in y equals 0. So I'm plugging in 0 for this output, and then we are solving for the x. Okay, and so x is up here in the exponent, and so my first step is to subtract 2. And remember, we're trying to isolate the exponential expression, and so the exponential expression is just this base and this exponent. And so the negative still needs to go. And so my next step is to divide both sides by this -1. And that leaves me 2 equals 4 to the x minus 5. Now, similar to the last example, 2 is technically 4 to the 1/2 power because it's the square root of 4. And a square root is the same thing as a 1/2 power. Remember, we're always trying to get a common base so we can avoid using the calculator and avoid using log. And so now that my bases are both 4, I can set the exponents equal to each other, which gives me 1/2 equals x minus 5. If you want to get rid of that fraction, you can scale your entire equation by 2. And then continue solving for x. So add 10, and then divide by 2. And then honestly, you could leave this as a fraction, but it does say if it's not a whole number, round to the nearest 10th. And this is a nice decimal, it's 5.5. And so that's what your calculator would give you as well. Okay, and so for the y-intercept, we are plugging in x equals 0. So going back to our original equation, this time our x is 0. And so that gives me negative 4 to the 0 minus 5 plus 2, which is negative 4 to the negative 5 power plus 2. And then whenever you see a negative exponent, leave the negative, but move the 4 and raise it to a positive 5th power to the bottom. Still trying to do all of this without a calculator. And so this is negative 1 over 4 to the 5th power is a very, very small number. Very, very small. And so if we were to plug this into our calculator, it's going to be approximately 2, because if you do 2 minus a very small number, it's still going to be close to 2. And in fact, I plugged it into the calculator and got 1.99, which does round to 2 as the nearest 10th. Okay. Next, we are going to find the max and min on this closed interval from negative 3 to 7. And so just picturing what this function looks like, we have negative 4 to the x minus 5 plus 2. It has a base of 4, so we know it's going to grow, but it's been reflected. Okay, and so if I were to sketch this, the horizontal asymptote is at 2, and the entire function is below it, reflected. Okay, so this is a decreasing function, decreasing. And so that means when I'm looking at the interval from negative 3 to 7, negative 3 to 7, our maximum is going to occur at the left endpoint. So we just need to plug in the negative 3. So the max at negative 3, because it's decreasing the further we go to the right. And so we are plugging in negative 3 to our function for the x, which gives us negative 4 to the negative 8 power plus 2. Once again, that's negative 1 over 4 to the 8th plus 2, which is very, very close to 2. And so if you were to plug that into your calculator, it's 1.99998. And so we would just say 2. It's getting very close to the asymptote at that point. Okay, now it's saying find the minimum, and it's the same interval, same function, and so this time we want to plug in the 7. So the minimum is at x equals 7. So taking our function, negative 4 to the x minus 5 plus 2, this time we are plugging in the 7. Okay, and so that gives me negative 4 to the 2nd power plus 2, which gives me negative 16 plus 2. That negative doesn't get squared, which is negative 14. And so our minimum value is negative 14, which of course is a lot lower than 2. And looking at this picture, that makes sense. If we were to plug in a higher number, it would be decreasing down to the negatives. All right, looking at this next example, to find the x-intercept, we plug in y equals 0, and we solve for the x. Okay, and so first we need to isolate the exponential expression. I'm just going to kind of box that off so you can see what's outside. So our first step is to subtract 3. And then we have to divide by this negative 3. Okay, and so that gives me the equation 1 equals 1/4 to the x plus 4. And I always love it when one side of the equation of an exponential function is 1, because you can always write 1 as any base, in this case 1/4 to the 0 power. Anything to the 0 power is 1, and so that's a trick. They love that on SAT. Okay, and so now I know 0 has to equal x plus 4, because I have the same base. Now I just subtract 4. Okay, and so my x-intercept is negative 4, 0. Okay, for the y-intercept, we are plugging in x equals 0. So going to my original function, y equals negative 3, 1/4 to the 0 plus 4 plus 3. Okay, and so that gives me negative 3 times 1/4 to the 4th power plus 3. And then 1/4 to the 1/4 power, you just take 1 to the 4th power, which is 1, and then 4 to the 4th power. And then when we multiply these fractions, the negative 3 would be multiplied by the numerator, which would give me a negative 3 on top, over 4 to the 4th power, which is 256, plus 3. Again, that is a very, very, very small number. And so we're subtracting a very small number from 3. And so if you type that in your calculator, it's going to round to 3. It's 2.988, which again rounds to 3. And so we would just say 0,3 after the rounding. Okay, now finding our max and min on this interval. So let's picture this graph. And so I have negative 3 to the 1/4 times 1/4 to the x plus 4 plus 3. This 1/4 base is going to decay. And so it would usually look like this. The parent function would be a decay function, decreasing. But it has been reflected across the x-axis. So now it is going to be upside down decay. And so that turns our function to an increasing function. Okay, it's increasing. That means my maximum is going to occur at the right endpoint. And that means my minimum is going to occur over here at the negative 5, the left endpoint. Okay, and so that just saves you some time so you're not plugging in both. So negative 3 times 1/4 to the x plus 4 plus 3. And we're going to do that same thing for the negative 5. And so looking at our first example, we have negative 3 times 1/4. Negative 2 plus 4 is just 2. 1/4 squared is 1/16. Negative 3/16 plus 3 If you type that into your calculator or turn it into a fraction, it's approximately 2.8. And so our maximum is 2.8. Over here, -3 times 1/4, -5 plus 4 is -1. And then 1/4 to the -1, that means reciprocal. So it's just 4 over 1, or just 4, which gives me -12 plus 3. Which gives me -9. Okay, and of course that is lower than the 2.8, so that is our minimum. And so if you plugged them both in Number Crunch, it takes more time, but you could still figure it out that way. Okay, for our last example, finding the x-intercept, we plug in 0 for y. And so that gives me 0 equals 2 to the -x plus 3 plus 5. And so looking at your exponential expression, we have to get rid of the 5. Okay, and so now I have an exponential equation, but I can't get a common base. There's no way to rewrite this -5 as a power of 2. And so this is when we have to use log. And this is the first example. So my base is 2, log base 2 of -5 equals -x plus 3. So log base 2 of -5 equals -x plus 3. Okay, saving the calculator for the very end, we would then subtract 3 from both sides. And so I have log base 2 of -5 minus 3 equals -x. And then we would just divide by -1. And so now in our calculator, we would do alpha math, log base 2 of -5. Oh, before I even type anything else, that's going to give me a non-real answer because the argument of a log cannot be negative. So we honestly should have stopped right here. You're not going to take an exponential expression and get a negative output, which is why your input of a log cannot be negative. And so right here, when you saw that, we should have stopped and said no solution. Okay, and so this function has no x-intercept. And just to picture this graphically, this is base 2 reflected across the y, so it's decay, but then it's been shifted up 5. Okay, and so we have a horizontal asymptote at 5, and then we have our entire function sitting above it. It's never going to cross our x-axis. Okay, and so that's kind of helpful to know where the horizontal asymptote is and where the exponential function is. If it's above the horizontal asymptote and it's up at 5, no x-intercept. Okay, so for the y-intercept, we're plugging in x equals 0. So taking our original function, 2 to the -x, which would still be 0, plus 3, plus 5. That's 2 to the 3rd, plus 5, which is 8, plus 5, which is 13. Let me write that properly. Okay, last we are finding the max and min. And so I already sketched the graph up here. We know it is growing but reflected across the y. So usually growing looks like this, but if we reflect across the y, it's going to look like decay. And so this function is decreasing. picturing a person going from left to right. He's going down the mountain. So my maximum is going to occur at the left endpoint. And so my minimum is going to occur at the right endpoint. Okay, and so taking our function 2 to the negative x plus 3 plus 5. Okay, and so plugging in the -1, plugging in the +3. And so for the -1, we get 2 to the -1, which is +1, plus 3, which is 2 to the 4th, and then the +5. 2 to the 4th is just 16, plus 5 is 21. Now this isn't an ordered pair, this is just a y value. Remember, max and min are just y values. Right, and then plugging in the 3, I get -3 plus 3 in the exponent, which is 2. 2 to the 0 is just 1. Add the 5, you get 6. Okay, and so my minimum value is lower than my maximum. That's encouraging. And so those are our max and min values.